Bismillahirrahmanirrahim. First of all, I'm grateful for this generous introduction. So when I was preparing for this talk, I have tried to keep the concepts of this talk a little bit more generic. And since I'm standing in the National Center for Physics, obviously I would like to emphasize more onto the physics aspects of MRI. The talk today is composed of two main sections. In the first section, I'll talk about the fundamental principles of magnetic resonance imaging. And in the second half, I'll tell you about the research activities we are doing, our participation in different international conferences, and our main areas of interest, so that you can be aware of our research activities, and we'll be welcoming any future research collaborations. That's the main objective of having this NASCOM lecture forum, to improve the collaborations between academia and industry. So with this, firstly, before getting on to the MRI, most of you will already know the difference between science, technology, and engineering, but I would like to highlight the main differences as per my own understanding, and then we'll relate it to magnetic resonance imaging. So we know that science is the discovery of facts, right? So when you are discovering the principles which Allah Almighty has set up in this word, that is science. Technology is the practical application of science. If you have discovered the fundamental principles and you want to use those principles for your own benefit, then it becomes technology. For example, earlier on, I mean, when radars were invented, before that people thought how sharks communicate with each other, and the principle which they found was that they send an echo, and then they send a pulse, and then when it's received back, the fundamental of the Doppler principle. So that's what Allah Almighty has already incorporated in the communication system of certain type of fish. So that knowledge of the principle is science. If you know the science, the next stage is you want to use it for your own benefit. And that's why, for example, in that particular instance which I mentioned about the fish communication, so we thought that how we can use that principle, and then we made radars. They work on the same principles, right? So that is technology. So you cannot do technology unless you have done science. So, and even our own teachings, this morning I was just going through Surah Ghashiyah, and the Quran Pak, I mean Holy Quran, it emphasizes a lot about you should contemplate upon afala yanzuruna ilal ibili kayfa khuliqat wa ila samai kayfa kayfa rufiyat wa ilal jibali kayfa nusibat wa ilal arzi kayfa sutihat. So I mean, these are all the verses which tell us that how we discover the principles which Allah Almighty has set in the universe. So that is science. So science and technology, both of these come together. And when you want to commercialize, technology, then it becomes engineering. So engineering is to design, create, and produce new tools, machines, and systems for practical human means by exploiting technology. When you want to optimize things, so when you want to develop mathematical models, how to reduce the cost, how to improve the system, how to improve the throughput, how to improve the efficiency of the system, that is engineering. So obviously engineering comes after technology. So all these three things are related to each other: science, technology, and engineering. Without laying the fundamental understanding of science, you cannot develop technology, and without technology you cannot do engineering. And obviously, I mean, engineering, we know there is a lot of mathematical models and those sort of things which come into play. Now, I mean, I would like to start my talk with an eagle story. That's an incident. That's a personal story. Just by the way, I mean, I was a Commonwealth scholar in UK. I was the only person from the whole country who was selected in 2008 as a Commonwealth scholar in engineering to do PhD in medical imaging, in particular MRI from Imperial College London. But the way to London was not that easy. I mean, when I was doing my engineering from Dawood College, Karachi, Dawood College of Engineering and Technology, Karachi, I learned Arabic and Persian language out of my own interest because I wanted to have a direct understanding of the Holy Quran and Hadith. For that purpose, I spent a lot of time, and I also did BA as a private candidate with Arabic, Persian, and Islamiyat in the summer holidays. And fortunately I got very good grades. Then I also joined MA Arabic at Karachi University in the evening when I was doing engineering in the morning. So the purpose of doing that, of learning Arabic and Persian was because, you know, Iqbal and Rumi and Jahiz, I mean, a lot of poetry and a lot of our treasure lies in Persian language. And at the same time, I wanted to learn Arabic because we could have direct understanding of the Holy Quran and the Hadith. But as soon as I completed my BEng, even my result was not announced. The first job I got was in Siemens Dubai. And the way I was offered that place was because they give an advertisement in the newspaper, and they wanted to have some people who are experts in sales of different control systems and, you know, different contactors and lighting products and stuff like this. And just even in my case, how to talk about the experience, even my result was not announced at that time. I just sent my CV, and then finally I was shortlisted and I was selected. Why? Because I knew Persian and Arabic language. In UAE, all the government transactions, they happen in Arabic language. So normally they were interested in me because normally they hire a translator and an engineer. Now, translator does not know about technology, about engineering, what he's selling, and the engineer does not know about Arabic. So there is a communication gap. In my case, it was there, and also I knew Persian because there had been a lot of Iranian customers who used to visit UAE and then purchase products. So by the way, I was posted in the light engineering department, lighting department of Siemens in Dubai. And one day, a Sheikh Saab came to, it was just couple of months when I started my job there in the lighting department. One of the sheikh came with an eagle on his arm, and he said that, you know, I need a fantastic light for my eagle. The light which was already there in the cage of the eagle is not working. It has stopped working. So please give me a light which nobody else in UAE has got. Now that's a common philosophy in UAE. People are very rich there. When they come to you to purchase something, they ask you to give something which nobody else in the whole UAE has ever purchased. So that guy, he came to the salesman first, and the salesman got, really confused. And since I was a sales engineer, a step higher than him, he came to me that a Sheikh Saab has come, and then he wants a fluorescent tube, and he says that the tube has stopped working, and he's saying, give me a fantastic tube which nobody else in UAE has got. I told him that charge him a good sum of money, and that's how these multinational companies teach us. I told him charge him a good sum of money and give him the best fluorescent tube we have got. So he took the tube, and then he came back after 3 days. This time he did not have eagle. So we realized there is something wrong with it now. And he came and said, look, I'm going to sue your company because since the time I installed that fluorescent tube in the cage of my eagle has gone mad. So there is nothing wrong with the eagle. What is wrong with your fluorescent tube? What you have given? So I'm going to sue your company. And we knew, because when we go to UAE, the first few lessons they teach us, first of all, they say that you never think of fighting with somebody who has a ribbon, because they are the nationals, right? Secondly, you cannot wear that ribbon, and don't disturb camels or eagles. They charge heavy fines if something goes wrong with him. So I was in serious problem because my job was quite new, and he was saying that since the time I installed that tube, your company's tube, so it is Siemens sells its products with the name of Osram. Osram is the lighting brand of Siemens actually. So I went to my manager. I said that, look, this guy has come and he's saying that since the time he installed our tube, his eagle has gone mad and he's going to sue our company. So, I mean, he said, well, let's take the equipment and let's go to the cage. Now, I'll continue on with that. Before that, all of you understand the principle of fluorescence. There are different types of light bulbs, right? And I did not appreciate it unless I spent a couple of years in the lighting department of Siemens, that there are so many different types of tubes: studio lighting, film lighting, mercury lights, fluorescent tubes, incandescent bulbs, so many different types. Fluorescent tubes, how do they work is, there is a pressurized gas, and there is cathode and anode, right? High voltage applied at the cathode, electrons emit the cathode, go towards anode. While passing through, they ionize the gas particles lying there, and after some time, those ions, when they come back to their original state, they give out light. This is what fluorescence is. Fluorescence works on this principle. So these fluorescent tubes, actually, they work on the principle of the continuous ignition of the ionic chamber, and then so what we feel actually is because of persistence of Vn. Because if we look at anything, its image stays in our eyes for about 1/16 seconds. Its impression stays in our eyes for about 1/16 seconds. So that's how the old cartoon movies were made. That if 18 frames pass in front of you, right? And for example, one picture is like this, the other one is like this, the other one is like this. So when they pass in front of my eyes with a speed more than 18 frames or something like this, I'll see as if my hand is continuously moving. So this was because of persistence of Vn. In the fluorescent tube as well, what happens, it has, it's 50 hertz, the frequency at which AC works here in most parts of the world is 50 hertz. So this fluorescent tube, actually, it's not continuously glowing. It is flickering. We don't feel it's flickering because of persistence of Vn, right? So because since our persistence of Vn is about 16 frames, so if something passes more than 16 frames, we'll see it's continuously glowing, but it's not the case of the eagle. Eagle has a very sharp Vn, and its persistence of Vn is much less than humans. So the mistake which we did was we gave him an ordinary fluorescent tube as per persistence of Vn of the humans. And what we realized, the fluorescent tube which was already installed there was the one which was operating at 200 hertz or something like this. So the fluorescent tube, we were thinking it's continuously glowing. When that fluorescent tube was installed in the cage of the eagle was seeing it on off, on off, on off, on off. And you imagine if somebody puts you in a dark room, right, and the light is continuously glowing like this, you'll go mad. And this is exactly what had happened with the eagle. Because the fluorescent tube was not made at that high frequency. So we apologized, and we ordered a high frequency tube from Germany, and it was installed, and after that the eagle was happy. So so now you understand the difference between science, technology. So you cannot solve the problems of real world if you don't know science. If you don't know the principle of persistence of Vn, which we study in our primary courses of physics or before our matriculation, you cannot give solutions to the real world problems. Science, technology, and engineering, all these things come together, right? Now let's come back to MRI. MRI is magnetic resonance imaging, and this is how the MRI scanner looks like. It's the most expensive equipment. One of the most expensive equipment in medical imaging. Recently, 3 scanners have been installed at CMH in Rawalpindi, and we work in collaboration with them. And the cost of the scanner before the dollar price hike was about something around 25 crore Pakistani rupees, something like this. So it's a very expensive piece of equipment. So this is how the MRI scanner looks like, but it's only the front end. Later I'll show you the different sections of the MRI scanner. But this is, this is, I say, the climax of engineering, because the patient is lying comfortably in it, and the wires, the coils which are there around in this, there is current of about 600 amperes, which is passing through this. So these coils, I mean, around the patient, they are carrying a current of up to 600 amperes sometimes. So it's such high, and you just imagine P equals I square R, how much heat dissipation and how much problem. But we have maintained different superconductivity levels. I'll talk about those later, which help to lie the patient in a comfortable environment. MRI is, and by the way, this is not open to sky. I went to Montreal for a conference a couple of years ago, and there was a company, they were selling these. These are the plastic sheets, and they have made it so that the patient does not feel claustrophobic, because one of the most important problems of MRI is, you just lie as if you are lying in a grave for such a long time. So the people who are claustrophobic there feel really uncomfortable about it. So in technology, when you are developing a technology, there are many associated products coming up with it. So that company is making these perspex, these plastic sheets, which give you the natural look of as if it's open to sky. Otherwise, there is proper RF shielding, proper caging, which has to be done to maintain the magnetic field within the scanner room, not beyond that. So why MRI is very useful? Because it gives you fantastic quality of images. So the quality of the muscles or the tissues in terms of resolution you can get from MRI, you cannot get it from any other imaging modality. Although CT is good, CT also provides you very high resolutions, but the problems are CT is very ionizing, right? So if you take 100 X-ray exams or you take one CT exam, both are equivalent in radiations. So CT is, there are many problems with it, but MRI it's completely non-ionizing. There are no hazardous ionizing effects of MRI whatsoever, and it gives such a high quality of MRI, of images, that you could, these images are even a little bit older, but in the modern technology you can see each and every vessel with so much clarity which you cannot see in any other imaging modality apart from MRI. So the MRI is very famous. It's itself, there are some specialized areas of MRI. There are hundreds of domains within MRI, and in the top universities of the world, every university is focusing on to one particular aspect of MRI. Right? So it's such a wide field. So coming back to the physics of MRI, MRI stands for magnetic resonance imaging. Right? So there are three facts involved in MRI: magnetism, resonance, and imaging. These three things together, they make up the technology of MRI. So it is magnetic resonance imaging is a spectroscopic imaging technique used in medical settings to produce images of the inside of the human body. So you actually effectively in MRI you have used magnetism, you have exploited or manipulated magnetism to produce the images of the human body actually. MRI is, as I said earlier, it's the short for magnetic resonance imaging. It is a procedure used in hospitals to scan patients and determine the severity of certain injuries, especially in the cases when the soft tissues are involved. The quality of imaging you could see with the help of MRI. No other imaging modality can provide you that much detailed information. So soft tissue injuries especially, they are very clearly seen with the help of MRI. An MRI machine, it uses a magnetic field and radio waves to create detailed images of the body. So it uses a magnetic field which is obviously very strong. I'll talk later, and some radio waves, RF pulses, which are in the megahertz range, to produce images, detailed images of the body. And the common reasons why people want to get an MRI scan are for sprained ankle or for back pain, or these days for neuroscience studies. I think in 2011 I attended a conference there was 1 week course in TU Delft, Technical University Delft in Netherlands, and the title of that workshop was Ethical Aspects of Engineering. and they had invited the engineers and the psychologists, because there is only one technology which can quantify what is going on in your brain, and that is MRI. No other imaging modality can provide you. If, for example, I mean, there have been certain instances. I understand, I have given a couple of lectures at Oxford University. Oxford University and MIT have jointly established a very big research center of neurosciences at University of Oxford, UK, where they are doing research where psychologists and engineers are working together. For example, there have been some instances. There is a lady, very rich lady in UK. She is always, I mean, she's in no short of money. I mean, there are no issues of money lack with her, but she always do stealing. She steals things from the superstores. There are some people, I mean, who write with their right hand, some people who write with their left hand, right? There are certain habits which we do. I mean, we don't know so what is actually different in the brain? There is a very big research center. So what technology they are using to quantify what is going on in the brain is MRI. And the name they give for that is fMRI, functional magnetic resonance imaging. So that is, slightly modified application of MRI. All is the same. So you can get functional information of the brain. Neurosciences is doing a lot of work. We later on I'll tell you, we ourselves at ComSats University, we did a project with the help of the World Academy of Sciences. We had a postdoc who came from Nigeria, and he got the funding from Italy. He stayed with us for a year, and we performed a study that how Holy Quran memorization affects your brain, how Holy Quran memorization affects your memory. We put the about 80 people in the MRI scanning process at CMH. We did the experiments, and we quantified what is there in the brain, how the brain of a Hafiz is different as compared to the brain of an ordinary Muslim. And so we made three groups. One is the Hufaz, who are more than 50 years of age, because dementia and memory loss diseases, they express themselves when you are older than 50 years. And the second group was day-to-day Muslims. They have memorized part of the Holy Quran and did not understand the other part, right? And thirdly, the non-Muslims. We did that in joint collaboration with CMH, and we had some experts involved from there. So we did proper sampling, we did the MRI. So what technology we used for imaging the brain there? MRI. Because MRI can provide you deep insights into the brain. I'll briefly talk about it later. So that is, it's not only the anatomical information you get, but it's also the functional information you can get. It's not only the functional information of the brain, it's the functional information of your stomach, of your intestines, how they're working. So people have started to use MRI for that. Now, this slide is a little bit controversial, and I realized it when one of my MS student, actually recently she was interviewed at a university in Barcelona for a PhD position. It happened just a couple of weeks ago, and then she added the contents of this similar to this slide, that it's all about water. MRI is all about this water, and the PhD she has been finally selected to the Barcelona position, and she'll be going there in a couple of weeks, inshallah. So when she presented this slide, the people who were there, they were more into the NMR. That's the 1D aspect, nuclear magnetic resonance. They are looking at the sodium ion concentration, potassium ion concentration, and stuff like this. So they went against her, that why you're saying it's all about water. MRI not only looks at water, it also looks at sodium, it also looks at potassium, it also looks at so many other ionic combinations as well. For example, we know that recently there is a use of MRI in arthritis detection. So because there are the deposition of certain ions which happen in the joints in the people people suffering from arthritis. So, while talking about it's all about water, because the most common use of MRI is the detection of water. That's why we say it's all about water. Otherwise, the modern applications of MRI are looking at some other ions as well. But then obviously the equations change, the RF pulse frequency change, everything changes, right? But the overall system, there is not a big change in the overall system. So mostly we use MRI to look into water, to look through water. So normally the common principle is any part of the body which has water content in it, you can take its MRI exam. But the parts of the body which do not have water content in it, you cannot take their MRI examination unless you do inject some contrast agent. You have to do some other interventions in it. So mostly, for example, the first imaging experiments performed with MRI were the brain imaging, and the brain is white matter, gray matter, or water-based tissues, right? So mostly, you could see that there is, because wherever there is blood, there is water, right? So and blood is almost in most parts of the body. So MRI scanners are able to see this water and construct an image. So MRI is fundamentally detecting the presence of water, right? Okay, now let's think about the chemistry of water molecule, that why only water molecule works with it. Firstly, hydrogen nuclei have a property to spin, so the people with background of physics will understand that the hydrogen nuclei have a property to spin. They spin around their own axis, and as a result, they produce a magnetic moment. Any moving charge will produce a moment because hydrogen is positively charged, right? So, it produces a magnetic field which is called magnetic moment. Okay, now before that, another thing we should remember is the water molecule has a dipole in it, because hydrogen and oxygen has a difference of electronegativity. We know that oxygen is highly electronegative. Its electronegativity, its ability to pull the shared electron pair towards itself, because there is a covalent bond between hydrogen and oxygen in water molecule, and oxygen pulls that shared electron pair slightly more towards itself as compared to hydrogen. So because of that, there is a slightly positive charge which appears on the hydrogen and slightly negative charge which appears on the oxygen. So it's that dipole which causes this magnetic moment to happen. So effectively, any ion or any atom which has dipole present in it, that will precess in the presence of a magnetic field. So even if you are looking at sodium imaging, for example, there are different isotopes of sodium. So the isotopes of sodium which have equal number of protons and neutrons in them, they won't wobble, they won't precess. But the ones which have uneven distribution of number of electrons, number of neutrons and protons, right? So there you'll see that they'll precess. So if we focus mainly onto water at the moment, so when hydrogen nuclei, they have a property to spin, and when they spin, that spinning field produces a magnetic moment, and this magnetic moment interacts with the magnetic field of the MRI scanner. Magnetic field itself, MRI scanner itself has a very strong magnetic field, and that magnetic field will interact with the magnetic field of that spinning hydrogen nuclei, and that interaction will produce the MRI signal, right? So okay, now we'll come back to water again, but let's discuss resonance. You must have heard in the Mughal history that there used to be Tansen. What was special about Tansen? Music. So what he used to do? जी, और फिर resultantly बारिश होती थी और ग्लास भी टूट जाता था, शीशा भी टूट जाता था, right? Why? Because of resonance. Resonance is a principle when the fundamental frequency, or everything has a natural frequency, right? So everything has a natural frequency, and if the natural frequencies of two objects, they match with each other, maximum energy transfer takes place, right? This is resonance. So probably जो frequencies वो तानसेन साहब produce करते होंगे, so those frequencies would be equal to either the natural frequency of the glass or some harmonic of the glass, because harmonic is simply the integral multiple of the fundamental frequency or the natural frequency of that particular object. So as a result of that, the glass would shatter, right? So it's exactly the same principle of resonance we use in MRI. So what we do is, resonance is actually the transfer or exchange. And by the way, I mean, I'll give an example quite often. कि आपको पता है, in the Holy Quran says कि क़यामत के दिन सूर फूंका जाएगा और सारे इंसान यकायक मर जाएंगे. So probably the frequency is because of resonance. कि वो जो सूर फूंका जाएगा उसकी जो its frequency will somehow be equal to the integral frequency of the human consciousness or whatever. Right? So resonance is all over around us. Similarly, the water molecules, when you put them in a very strong magnetic field, they have certain, they start wobbling, they start moving around it on axis, right? But they start moving at certain frequency, right? If you know the frequency, the natural frequency of the water molecules at which they are wobbling, and you produce the RF wave which is equal to the fundamental frequency of those water molecules, what will happen? Energy transfer will take place. If you have a transmitter antenna, and that transmitter antenna is giving out the RF pulses at certain frequency, right? And obviously, it's just like, the resonance principle could be, for example, I have my mobile phone. Everybody has the mobile phone. There are many signals around us at this time. But if I have a U-phone SIM, I'll receive only the signals of U-phone in my mobile phone. It's why? Because of, the way the filtration system, the signal processing has been processed in it. Similarly, in resonance, it exactly happens in the same manner. There are some teachers, for example, in your life you must have come across. There are some teachers जो कि आपको पढ़ाते हैं and you understand everything. होता है या नहीं होता? And there are some people जिनकी शक्ल देख के ही गुस्सा चढ़ने लग पड़ता है आपको. Right? And you can't understand even a single word from them. Why does it happen? Perhaps because of resonance. सांप जो है वो बीन पे डांस करता है. Why? It likes it. Perhaps because of resonance. Right? So resonance is all around us. So when the protons, they are precessing at certain frequency, and you produce an RF pulse which is equal to the fundamental frequency or natural frequency of those water molecules which are wobbling there, what will happen? Maximum energy transfer will take place. So water molecules will absorb that energy, right? So this is resonance. So it's just like as if you're talking someone on your cell phone. There are so many people, sitting in this room, but I call a particular person, right? Obviously, I'm tuned only to that person, not to anybody else. It's exactly what happens in resonance. There are so many molecules, but if they are not equal to the natural frequency of the fundamental frequency of the RF pulse you're transmitting, no energy transfer will take place. Right? It's just like, in electrical engineering as well, we also study that loading effect, and all those sort of things. It's all similar to that. So in magnetic resonance, only the protons with the same frequency as the RF pulse will respond. So you have a transmitter antenna, right? That's why the transmitter antenna and the receiver antenna, so MRI owes so many things to communication engineering, because all the principles come from the communication engineering. Antennas, transmitter antennas, receiver antennas. So your transmission coil, what does it do? It gives out the RF pulses of certain frequency, let's say 63 megahertz or 64 megahertz. And you have calculated it because of physics and mathematical models that this will be the frequency at which the water molecules will be wobbling. You produce that RF pulse at that particular frequency and you transmit it. So the protons will absorb. Those protons will be protons are everywhere. They are in the fats, they are in the blood, they are in the liver, in every part of the body, and in different chemical environments. They exist in different chemical environments. But wherever they are, they'll receive that energy. It does not depend upon which particular chemical environment they are in, but since they are water molecules, इसी तरह से जैसे if you are a Pakistani, does not matter whether you are in USA or you are in UK or you are in Canada or you are anywhere. जब भी कोई कहेगा पाकिस्तान तो आप कहेंगे जिंदाबाद. Right? So it's just like the water molecules, they lie at so many different environments, so many different chemical environments, but wherever they are water molecules, they'll absorb that energy. So during the RF pulse delivery, nuclei become excited. So what will happen? The protons, when I say hydrogen nuclei, I say proton. So proton means hydrogen nuclei. So hydrogen nuclei, they absorb that energy. Right? So when they absorb that energy, they become excited. But RF pulse will be there for a very short instance of time. Right? And after that time, RF pulse will be turned off. So what will happen to the absorbed energy? That will be released. So when that energy comes back out, we absorb that with the help of, or receive it with the help of RF receiver coils. And that is what makes the MRI signal. In MRI, what you're doing is, first of all, you gave the RF pulses. Those RF pulses were absorbed by certain water molecules. And after some time, that absorbed energy was released. And when that energy was released, it was received by your receiver coils, by your receiver antennas. And that you use to make the MR image. Okay, so I'll explain that with the help of a diagram as well. So, initially they were at equilibrium. You excited them with the RF energy. They went to the higher energy state. And after some time, when the RF pulse is turned off, they come back to their original equilibrium state. And while coming back to the equilibrium state, they release that energy which they actually absorbed. Now, what's the catch? The catch is the rate at which that energy will be discharged. It depends upon the chemical environment where the water molecule lies. If that water molecule lies in the blood, the rate of its discharge of energy will be different. If it is in the fats, the way it discharges energy is different. So that is what produces contrast in MR image. You are giving energy to the water molecule which lie in different chemical environments, right? It's just like आप कहते हैं कि आप किसी दोस्त को कर्ज देते हैं, ठीक है, कर्ज आपने 10 लोगों को दे दिया मगर वापस हर एक ने अपनी मर्जी से करना है, ऐसा ही है ना, अपनी नेचर के, कोई आपको फौरन वापस कर देगा, किसी को आपको 10 दफा कॉल करनी पड़ेगी, right? So it's just like the RF absorbed energy will be given back, it will be discharged at a different rate, and that is what produces the contrast. उसी तरह से आप अपने दोस्त और दुश्मन, अपने दोस्त को पहचानते हैं ना, कि जिसने फौरन वापस कर दिए, आपने कहा भाई ये मेरा बड़ा सिंसियर दोस्त है, देखो मुझे जरूरत पड़ी, इसने, मैंने इसे कहा, इसने वापस कर दिए. कुछ ऐसे जैसे 20 दफा कॉल करेंगे फिर भी शायद वो कहेगा यार ये हो गया वो हो गया, right? So that's, you produce contrast among different types of your friends, just like this MRI produces contrast between different types of tissues. Okay, so this is the pictorial description of what happens. First of all, in MRI, there is a very, very strong magnetic field, right? So that when you put the patient in a very strong magnetic field, right? So that strong magnetic field produces it. When there is no magnetic field, let's say your magnet is switched off, the hydrogen nuclei are randomly aligned. They're not aligned in a particular direction. But when you turn on the magnetic field, the external magnetic field, when you turn on the external magnetic field, the hydrogen nuclei align themselves along the magnetic field. Some align parallel and some align anti-parallel. It's just like if you are going to UK, a couple of years back, मेरे कुछ students say they were going for a conference in UK. आर्ट द स्टूडेंट्स से. सो उन्हें मैंने कहा अपने रिलेटिव्स के एड्रेस वगैरह लेके जाना. नहीं सर, हमारे पास फंडिंग है, सब कुछ है, हम तो होटल में स्टे करेंगे. मैंने कहा फिर भी मुश्किल वक्त में रिलेटिव्स के नंबर आपके पास होने चाहिए. अच्छा, अब हुआ ये कि किसी पाकिस्तानी के थ्रू बुकिंग करवाई थी उन्होंने चीट कर लिया. वो जो बुकिंग करवाई थी वो वहाँ जाके देखा कि वो होटल था ही नहीं वहाँ पे एक्चुअली. अब वो रिश्तेदारों के नंबर ढूंढते रहे. ये डॉक्टर हसन गए थे उस वक्त साथ ही इन एडम्ब्रो. सो द पॉइंट इज, इफ यू हैव मनी, आप कहते हैं भाई मैंने अपने किसी रिलेटिव के पास नहीं रहना, मैंने तो अपनी एनर्जी शो करनी है, मैंने तो भाई अपने होटल में रहना है, 5 स्टार होटल में रहना है, राइट? और अगर आप बड़े वो हैं, बड़े क्या कहते हैं, बचत करते हैं, ऑब्वियसली से भाई जब मेरे पास अपॉर्चुनिटी है तो मैं क्यों होटल में पैसे जाया करूं. सिमिलरली सम प्रोटॉन्स, सम न्यूक्लियाई, वो कहते हैं भाई हमारे पास तो एनर्जी आ गई है, यानी हम तो ज्यादा एनर्जेटिक हैं, हमने तो सीधे नहीं खड़े होना, हमने टांगे ऊपर करनी है, सर नीचे करना है. Right? So they are aligned. When you put the patient in the MRI scanner, some protons align parallel, low energy, भाई जो stream this direction में जा रही है आप उसी direction में float कर रहे हैं. और कुछ कहते हैं नहीं जी हमने तो opposite direction में करना है, मैं ज़्यादा energetic हूँ. Right? So some protons, some align parallel, and the ones, especially the ones who have high energy, and some align anti-parallel. Right? They go against the stream. So this is no external magnetic field applied. So you could see all the water molecules in the patient, they are randomly aligned. They don't align in a particular direction. But when you put them in an external magnetic field, some align, this is the direction of the magnetic field. And by the way, the magnetic field we are talking is more than 25,000 times stronger than the Earth's magnetic field. जिस magnetic field में patient को place किया जाता है, there will be a slide later, I'll explain that. We are talking about a magnetic field which is 30,000 times stronger than the Earth's magnetic field. So in the presence of that magnetic field, what happens is some protons align parallel and some align anti-parallel to the external magnetic field. But normally there are more who are in parallel and very less who are anti-parallel, right? Because there are very less people who go against the stream. Otherwise everybody wants to get along the stream. So now what happens? So you put the patient in the scanner, and the protons, some of them aligned in the parallel direction, some aligned anti-parallel direction. Now the RF pulses are applied. So you applied an RF pulse through a RF transmitter antenna. Only the protons with the same frequency as the RF pulse will respond because of resonance, right? Or one thing, I won't go into very much detail of the detailed physics of it, but actually what happens is you produce a varying magnetic field throughout the body. In a पूरी body में एक ही magnetic field तो नहीं लगा होना चाहिए ना. Obviously it should vary, because sometimes you want to image knee, sometimes you want to image the heart, sometimes you want to image the head. So the magnetic field exposure of the head should be different as compared to, there should be a slight variation, right? Why? Because the frequencies should be different. So that if I want to image the knee, I say, well, this is the frequency at which I should give the RF pulse. And by the way, MRI scanner calculates all this. It knows that which frequency I should produce. You just choose the anatomy of interest. It calculates the magnetic field by itself. It calculates the RF transmitter frequency by itself. But it's not very much varying. For example, as part of my PhD, I myself designed a transmitter coil and the receiver coils as well. So we were operating for 1.5 Tesla scanner. We were operating something around 63 megahertz. That was the central frequency. और फिर उसमें plus or minus होता था 0.5 megahertz or minus 0.5 megahertz. So the range of frequencies used to be something around between 62 to 64 megahertz, not more than that. Right? So that much variation, and it depends. And the scanner tells you, if you want to image the knee, this is the frequency you should produce. If you are imaging the heart, this is the frequency you should produce. So only the protons with the same frequency as the RF pulse will respond. So it means that if you want to image the knee, your scanner will tell you, you'll just choose the knee, and the scanner itself will calculate that the protons or the nuclei, water molecules which lie in the knee, what frequency they have got. It will produce the RF pulse of that frequency. So when that RF pulse will be transmitted, only knee will absorb it. Only the water molecules in the knee will absorb it because of resonance, because everywhere else the frequency is different, right? So, and by the way, how that frequency is calculated? It's calculated on the Larmor equation, and that is omega equals gamma b, where omega is the resonance frequency, gamma is the gyromagnetic ratio, and b is the magnetic field. So what does it tell you? It tells you that if it's 1.5 Tesla scanner, b is 1.5, omega will be different. If you increase the strength of the scanner, 3 Tesla scanner, omega will be a different number. So it means that when you are designing your system, when you are designing the transmitter coils or the receiver coils, you have to be careful about which frequency you are talking. This is designed for which particular scanner. For example, I remember once I visited University of Nottingham, and Nottingham has a fantastic medical imaging facility. One of our PhD students is going there recently in a couple of weeks' time to spend 6 months, because Peter Mansfield, he established that center and he won a Nobel Prize as well. So the first 7 Tesla MRI scanning facility in the whole world was installed at Peter Mansfield Center at University of Nottingham. And I remember that वहाँ पे एक PhD student, his only research was to produce a wrist receiver coil, जो कि आप सिंपली टैंक सर्किट से बड़ी आसानी से एक कैपेसिटर और इंडक्टर को पैरेलल में रख के आप बना सकते हैं या सीरीज में रख के बना सकते हैं. और उसकी पूरी PhD इसके बारे में थी, because it becomes so much tricky in such a strong magnetic field. 7 Tesla, as part of his whole PhD, he developed a wrist coil to image the wrist of the human body right, which will be able to receive the signals of 7 Tesla MRI scanner. Because I mean, he had to develop so many models and he had to do so much work. Okay, that's one thing. So B, what's the resonance frequency? It depends upon the value of B, what magnetic field strength you're talking about. Right? So next time, if you happen to, or if some of your relative needs to take an MRI examination at CMH hospital or at IDC or whatever, you should ask them to take the MRI scan of a higher magnetic field, because that provides better contrast, better information. I mean, you pay the money at CMH and it's up to them whether they scan you on 1.5 Tesla scanner or they scan you on 3 Tesla scanner. Or if you go to Shifa, they have a permanent magnet scanner which is 0.73 Tesla or 0.47 Tesla scanner as well, the old scanner. So that obviously will produce low resonant frequency and resultantly low signal to noise ratio and low contrast. So it won't help, it may not help very much to the radiologist. Okay, so the value of omega depends upon the B. It also depends upon gamma, and gamma is constant. Gamma is constant for water. If you want to image sodium, then gamma will be a different value. So that's why I was saying that it's all about water is true if you want to image the human body. But if you are interested in sodium imaging, then the gamma value for sodium will be different and omega will resultantly be different. So you have to design a modified scanner. So this equation is actually very useful to calculate the resonance frequency. So the absorption of the RF energy changes the energy state of the low energy hydrogen nuclei. If you remember that diagram which I showed earlier, some protons parallel and some anti-parallel, right? So the protons normally which are in the low energy state, they absorb that energy. Right? They absorb that energy and they go to higher energy state. So this is exactly what is shown here. So initially, if you remember, they were more in the low state. Now some of them, these two which are shown by these dotted lines, they absorbed that energy, right? And since they were at resonance, they went to high energy state. Pink color shows that the energy is on. So RF pulse is being transmitted. So when the RF pulse is turned off, what will happen? The ones with the high energy state, they'll come back to the equilibrium state, right? So when they come back to so high energy nuclei prefer to go back to equilibrium when the RF pulse is turned off, and they release the energy in the form of electromagnetic waves. And those electromagnetic waves has a receiver coil, MRI machine has a receiver coil that receives the energy, those energy waves which are discharged. And what is the catch? As I said earlier, the catch is the rate at which energy is released, it is different for different chemical environments. If the water molecule lies in the fats, it will give out that energy at a different rate. If it lies in gray matter or in white matter, it will release the energy at a different rate, and that is what will produce the contrast. Okay, now Fourier, I say MRI is the climax of engineering because Fourier has helped a lot. Because in MRI, the signals which came out, the signal which you received, you have to apply analog to digital sampling, and then you have to store it in a matrix, and that matrix is known as K-space. So to produce an MR image, you have to take inverse Fourier transform of that K-space. So that is actually how MRI is different. In CT scan, you don't do that. In X-rays, you don't do that. In X-rays, you are simply producing a reflection. The same process you are doing in CT as well. But in MRI, the acquired data and the image are related by Fourier transform, right? So when the emitted energy is received, the data is mapped onto a matrix which is called K-space. The K-space can be transformed into wave functions because, I mean, you know that what Fourier said. Fourier said that, I mean, sine and cosine waves can be used of different amplitude, frequency and phases can be used to model any signal, 1D or 2D. So that is actually how we are using that concept in MRI. So the K-space can be transformed into wave functions representing different frequencies to give us a high resolution image of the body. This is the entire picture. First of all, what happened in the first stage? Atoms spin in random directions like tops around the individual magnetic fields. In the magnetic field, when you applied the external magnetic field produced by MRI, atoms line up either north or south, either parallel or anti-parallel. About half the atoms go each way, but there are a few unmatched atoms. Like in the previous example, we said there are more in the absence of RF, before the application RF pulse, they are more in the low energy state, more in the parallel direction, and less in the anti-parallel direction. But when you gave the RF pulse, they are more in the anti-parallel direction and less in the parallel direction. There is a net difference anyway which produces the MR signal. So when the radio frequency pulse is applied, the unmatched atoms spin the other way. So more of them go to the high energy state. And then when the radio frequency is turned off, the extra atoms return to the normal position, emitting energy, and that energy you received, applied A to D sampling as per Nyquist criteria or using some other method or some other sampling rate. And then as a result, you acquired the MR image by applying inverse Fourier transform of the on that acquired K-space. So that is the entire picture, how the MRI physics works. I hope, I made the point clear, right? So now let's go to some more, some of you might have bored, so let's go towards some interesting facts about MRI. The Earth's magnetic field is about 0.5 Gauss, and the magnetic field which we use in MRI is 5,000 to 30,000. And actually these figures are old because these days 7 Tesla scanner has also become clinical, right, in many parts of the world. Although mostly it's 1.5 Tesla or 3 Tesla, even at, the one which is in the Islamabad Diagnostic Center in F8, they have got 1.5 Tesla scanner. They have recently installed it. However, at CMH in AFIDI, Armed Forces Institute of Radiology and Imaging, we have got 1 3 Tesla scanner and 2 1.5 Tesla scanners. At Shifa International Hospital, they have got 1.5 Tesla, not more than that. So 3 Tesla is, 1.5 Tesla works in most parts of the world. However, some very high quality imaging centers, they have got even 7 Tesla scanners. So this number will get even higher. So you could just imagine that we are talking about a very, very strong magnetic field. Maintaining such a large magnetic field requires a good deal of energy, because you have to, either you go with the permanent magnets. Permanent magnets cannot give you that high magnetic field strength. The permanent magnets can give you something around 0.45 Tesla. I said that at Shifa International Hospital, they have got 0.43 Hitachi scanner. That's it, 0.43 Tesla Hitachi MRI scanner, because that's working on the permanent magnet case. However, to produce high magnetic field strengths, you have to use electromagnet. And in electromagnet, you have to give in electrical energy. Only then you'll produce the magnetic field, right? So maintaining such a large magnetic field requires a good deal of energy, which is accomplished by superconductivity. Because otherwise, you imagine that 400 or 500 amps, the patient will just boil off. Because of, you can't operate the things at room temperature. You have to maintain superconductivity. Why? So that it reduces the resistance in the wires to almost zero. And by the way, the length of the wires which are around the scanner, in the scanner when the patient is lying, that goes a few kilometers. It's a very long length of copper wires there. All of them needs to be properly bathed in helium. Why? To maintain superconductivity. Because sometimes a phenomenon happens when even a slight part of that wire is not fully bathed in helium. What will happen? It will start giving out heat, and that heat will boil all the helium, and there'll be a blast. And that is known as quench mechanism. That's a safety mechanism at almost every scanning facility. But one of the main operational costs of MRI scanner is you have to continuously refill helium, and helium it's quite a few hundred liters of helium we are talking, right? Which has to go into that core where the wires are there. However, you know that in material physics, I know that there is a very big research center at Cambridge and a couple of universities in France. They are trying to build up materials who can maintain superconductivity at room temperature. If that could be possible, it will be a great revolution also in MR imaging, because then you will be able to produce the MR images without inserting any helium. But until then, you have to maintain superconductivity. To do this, the wires are continuously bathed in liquid helium at 452.4 degrees below 0 Fahrenheit. Right? So 269.1 degrees Celsius below 0. So minus 200, you have to maintain about minus 269.1 degrees Celsius, because I think just beyond that is the boiling point of helium. So you have to make sure that the temperature of the wires stay below the boiling point of helium, because otherwise if you forgot to refill your helium for a day or for some time, and even 1 millimeter of copper wire came out of the helium, what will happen? It will start giving out of heat, right? And then it will just go on. And you know that 1 liter of liquid produces how many liters of gas? Boyle's law, 24 decimeter cube, 24 liters of gas. And you're talking about hundreds of liters of gas. Hundreds of liters of liquid helium. If it turns into gas, how much pressure it will develop? Right? For that, there has to be a safety mechanism. They always have a safety quench mechanism, a quench pipe, which has to be going out of the MR facility to to avoid a blast of the MR scanner. But I mean, that's a very, very strong safety procedure. Okay, so how does since MRI, so the diagram, the beautiful picture which we showed, that was just the front end of MRI scanner, because it's such a complicated hardware, it's such a complicated engineering product. So you have to have you have to have PLCs, fully programmable logic controllers, which control each and every parameter of the MRI scanner, because it's not only the permanent magnetic field you have to control, it's also the 3 gradient fields. Now another benefit which I did not mention earlier is MRI can produce 3-dimensional imaging. You can produce any angle of the image without moving the patient. In X-rays you can't do that. For example, you must be doing X-rays, you have to stand in at that particular angle if you want to produce. In MRI, no. The patient just lies there. You can just control with your computer which slice, whether you want to produce this slice or 2D or 3D, whatever. So that's the beauty. And how do you do that? By the application of gradient fields. It's not only that permanent magnetic field gradient you're talking, it's also the 3 gradient fields. Although the permanent magnet is producing the magnetic field strength which goes in Teslas, but the gradient fields, they're producing the magnetic field strength which is milliteslas per centimeter. It's about 1,000 times smaller, because you have to produce slight variations depending upon the parts of the body you want to image. So, but for that, it's 3 gradient fields which will produce that variation depending upon, so that the resonance frequency changes of the parts of the body. So this axis shows. So MRI pulse sequence, it's a mechanism, it's a process which shows that which magnetic field will be applied at what time. So here you could see there is one RF pulse, that's the excited pulse I was talking, excitation pulse, and then you have 3 gradients, GZ, GX and GY. These gradient fields are just these are some other coils which are producing variation of the magnetic field in the x-axis, in the y-axis and in the z-axis. Although that variation goes only in milliteslas, it's much smaller, but it has to be precise. And actually, if anybody has ever taken an MR examination in this hall, MRI हुआ कभी किसी का, MRI scan करवाया कभी किसी ने? There is a loud banging noise, बहुत ज़्यादा शोर आता है, right? So that noise is because of these gradient coils, because a very huge amount of current is passing through it. And when current passes through a coil, there are Lorentz forces. So the wires actually, you have to keep them very stationary. It's such a strong magnetic field. Although one of our research collaborators at Case Western Reserve University, USA, they have developed a recent research in which they have turned that noise of gradient coils into music. ये just couple of years ये research publish हुई थी. They have turned that noise into music. उसी noise से उन्होंने music बनाया, right? But it's not commercial yet. I'm sure that first they'll make a patent, they'll investigate it, patent होगा, फिर वो they'll sell it, and then. So these three gradients, GZ, GY, GX, so these are so one is the permanent magnetic field जो आपने apply किया. Then there are three gradient fields in the x-axis, y-axis and z-axis, and then there is RF pulse which you applied. So this is the case space where you want to store data. What happens is the GZ is known as the slice select gradient. That gradient chooses which part of, when you select, I want to image my knee, so that slice select gradient will choose that particular value which is suitable for the knee, so that their resonance frequency maintains. It's all there inside the MR scanner programmed. RF pulse and the slice select gradient, they are applied at the same time. And then there are two other gradients. Well, this is known as the frequency encode gradient. I won't go into very much detail, but this is the phase encode gradient. It's just like, its concept is just like the polarization concept of light. आपको पता है light different directions में polarize हो सकती है, in x-axis, y-axis and z-axis, right? So just like this, you want to, or in communication we say phase shift keying and frequency shift keying. It's just like this. This is frequency shift keying and this is phase shift keying, right? Because you want to when the signal comes out, you want to identify which part of the matrix, in which row and which column of the K space you need to place that signal, and that is controlled by GY and GZ as well. So what happens is you applied the RF pulse at the time when you applied the slice select gradient, and the signal was produced. Protons absorbed energy of a certain location, then they gave out that energy. The echo came out. You applied A to D sampling at this stage at the time of frequency encoding, and you got one line of K space, right? Then what you have to do? So as a result of one application of the RF pulse, you were able to only fill one line of the K space. Then you have to repeat the same process, but this time you apply a different phase encode gradient, and that will take you to a different location in the K space, and you will be able to fill the second line of K space. And then what will happen? You have to apply a range of phase encode gradients, and as a result of that, you will be able to fill the whole of the K space. And this is why MRI is very time consuming. It's beyond human control. You're giving an RF pulse, tissue is absorbing it, then it is releasing that energy, and you are receiving that. You can't request the tissue, please give out energy quickly, I'm in a hurry. You can't do that. It's the biological principle. The energy will be, it's just like capacitor will charge in certain time, it will discharge in certain time. You can't do anything with it, right? So that's why MRI is a very time consuming process. However, sorry, yes, please.
Sorry to interrupt.
Yes, sure.
You just mentioned this is a time constraint for the travel time between the phase. Is there any trade-off between the processing part of the processors? For example, if you have installed FPGAs and for example, if you have installed different DSP and FPGAs there, is there a limit for their processing power as well in this delay?
No, there is no limit. We are talking about data acquisition at the moment. We are also doing a lot of work in FPGA designing. We have also filed a patent in USA about one of our inventions, but that is only the offline processing. Okay. At the moment, you're talking about the patient. The problem is the patient is in this scanner. You have to keep him in the scanner unless you acquire all the data. The processing comes at a later stage, right? And that is actually what my research group is doing, what we are doing. What we do is, the only way you could deal with this delay in data acquisition is either you acquire less number of lines. If you acquire less number of lines, obviously you'll have to apply less number of RF pulses. But the problem will be the Nyquist criteria. Because Nyquist criteria says that the sampling frequency should be at least double than the frequency of the maximum frequency you want to sample, right? And if Nyquist criteria is not met, that will produce aliasing, that will produce artifacts in the reconstructed image. Or the second thing you could do is you increase these gradients very quickly. There should be steep rise of the gradients, but then there is a problem. The problem is human body also has, we are also conductors, right? So if you are a conductor, and you know from Faraday's law that either the magnetic field changes, or the conductor which is cutting the flux of the magnetic field, that changes, currents will be induced, right? So that's why if you are in a 7 Tesla scanner room and you start walking through it, you will feel dizziness, Why? Because your body is a conductor. It's just like wire cutting through the magnetic flux of the magnetic field of the scanner, right? So the eddy currents which produce, they interfere with the frequencies at which your brain is working. That's why you feel dizziness. That's one limitation of the strong magnetic fields, right? So that is known as, in terms of physics of MRI, we say that it's the peripheral nerve, PNS limitation, peripheral nerve stimulation, because our peripheral nerves, the nerves that are periphery, I mean, they actually, if you increase the gradients, if you, for example, if you quickly change the gradients, if your electronics is technically advanced, and you say that, look, I'm going to take the gradient to a very high value in very less amount of time, the problem will be of PNS. Patients feel uncomfortable. So the only way left is you have to reduce the number of lines. That will produce the earliest images. Then you have to develop some advanced reconstruction algorithms to reconstruct an earliest image from that earliest image. And that is where the FPGAs and the power of GPUs comes in. Because then you'll be obviously using advanced interpolation techniques or some other methods, because you want to estimate the missing lines, but that will be done offline. Right? So does it answer your question?
Yes.
Right? So this is, so you got all this case space, and I think now you get a clear idea that why it's very time consuming to take an MR examination. And then you apply inverse Fourier transform of this acquired case space, and you get an MR image. So that's why I say it's the climax of engineering. MRI is the climax of engineering because it involves so many things. So this is how the MRI scanner system looks like. The patient comes only into this magnet room, right? And by the way, earlier I was saying it's a very strong magnetic field. It's a very strong magnetic field. And as you get closer to the magnet, to the bore where the patient is lying, the magnetic field gets really strong. And I remember when I was doing my experiments at St. Mary's Hospital in London, that's a teaching hospital of Imperial College, my glasses used to have a very, they were made of an alloy which will have a very small ferromagnetic material. And what used to happen, my glasses will get like this. अब फिर मुझे वो पकड़ के वापस पहनना पड़ते थे. I mean, it's a very strong magnetic field, right? So you can't even think about having any ferromagnetic objects inside this scanner room. So this is the main magnet room where the main magnet is, and there is a control room. This is where the people are sitting who are controlling the RF pulses. This is the reporting room, and this is the technical room where you have the PLC, programmable logic controller, big computer system which is controlling all the currents and everything about it. And then they are there. So I mean it has to be a big facility. MRI has to be a big facility. So this is, I mean, the people who have been to the scanner room, they'll know that this is where the magnet is, the main magnet is. And one another thing which I would like to mention to draw your attention to is the homogeneity of the magnetic field. We'll have done the experiments. We do it in the physics courses in our primary or metric, where you have those bar magnets, उनके दरमियान magnetic field lines draw करते हैं, so they are uniform only in the center. As you get to the outskirts, they become non-uniform. That's a big limitation in MRI, that you want to have a homogeneity, because otherwise your Larmor equation calculation will get wrong, because the resonant frequency will change, and as a result, the whole calculation will change. Maybe you might end up, you want to image the knee, and you might end up imaging your foot. Right? So you want to have a homogeneous magnetic field. For that you have shimming and so many different processes which have to be maintained, because it's really a challenge to have a uniform magnetic field. This is how the MRI scanner looks like. That these are the radio frequency coils and the gradient coils. I said that there are 3 types of gradient coil. The patient is lying there, and it's actually in these gradient coils that 600 ampere or even more amount of current is passing through. So it's actually huge. This is the equipment of MRI that, I mean, this is the small animal scanner which is shown here, but I mean, these are the gradient coils, RF coils, transmitter coils, receiver coils, and so on. There are different types of MR scanners, closed and open MR scanners. So one of the challenge, I said, if you want to have high magnetic field strength, which obviously you would like to have, you have to use an electromagnet. For electromagnet, it will be a closed magnet like this. At CMH, 1.5 Tesla scanner, 3 Tesla scanner, all those scanners are the closed magnet. although I went to the conference of our society, ISMRM society, the annual meeting was in Paris last year in July, and there they presented a special scanner for the US patients, because US में आपको पता है एक तो खाना बहुत खाते हैं, दूसरा वो मोटे बहुत होते हैं. So they made a closed scanner which was, they said, I mean, which is very big, but still problem is जैसे जैसे आप उसको वाइड करते जाएंगे homogeneity के problems आते हैं. It's difficult to make a homogeneous magnetic field. So it's otherwise, I mean, the animal scanners, I mean, mouse छोटा सा होता है, उसके scanners आप देखें, they maintain up to 13 Tesla, 14 Tesla, there is no problem of homogeneity, right? और फिर उसमें दूसरे problems भी होते हैं. दूसरा problem क्या है? Homogeneity, you can just imagine how complex the process is. भाई किसी के अंदर fats ज़्यादा है, वो disturbance create करेगा कि नहीं करेगा? अब दो इंसानों के दरमियान एक जैसा फैट तो नहीं होता, कोई मोटा है, कोई छोटा है, राइट, कोई पतला है. Everyone has got different physique. So the scanner, that's why when you put the patient in the scanner, the scanner does its calibration. It tries to calibrate itself, that what type of person is in, and then it calibrates its, I mean, there are so many variations. So that's the problem, that you have to stay in the scanner for a long time, and it's closed. The other thing, this is the open scanner. The person feels very comfortable, but the problem is this is the permanent magnet. At Shifa International Hospital, Islamabad, they have, as I said, Hitachi scanner, 0.43 Tesla perhaps. That is the open. But the problem is it takes a very long time. एक चीज़ और याद रखिएगा, जितनी scanner की magnetic field strength कम होगी, it will take longer for you to scan. Patient 2 घंटे तक पड़ा रहेगा वहाँ पे. Right, and even then it won't produce a very high quality SNR. Radiologist के लिए हो सकता है उसका कोई फायदा ही ना हो. Right, so although recently MRI has seen a greater use in the interventional MRI. आजकल people have started using MRI during the surgeries, during the operations. Right, at that time the surgeon needs to have access to the patient. Then obviously this does not work. Then you have to go for the open scanner. Right, so there are pros and cons. It does not mean that they are totally out of use. They are used these days as well, but it depends upon what use you are talking about. Few things about safety. All MRI magnets have a very strong magnetic field that extends into the exam room. Anyone entering the MRI scanner room will be exposed to the magnetic field attraction of the scanner. And I said it's a very strong magnetic field. We are talking about 30,000, 35,000 times stronger magnetic field than Earth's magnetic field. The closer you get to the scanner, because it follows inverse square law, right? So the closer you get to the scanner, the strength of the magnetic field becomes greater, right? And the problem is, I'll show you in the next slide, that any ferromagnetic object brought into the MRI scanner room will become magnetized. क्योंकि आपको पता है ferromagnetic material, once it becomes magnetized, it will retain its magnetism. That's why it's ferromagnetic material, right? So any ferromagnetic material will be attracted to the MR scanner, and the problem is it will not only be the linear projectile, it will be twisting around its own axis as well. तो वो कहाँ पे strike करेगा? सीधा patient के सर पे, because the patient will be lying in the center of the magnetic field. So any object going towards the magnetic field, it will not only be a linear projectile, it will have its torque as well. It will be twisting, so it will have a very high impact. So that's why I don't know about in Pakistan, I mean, although there are safety precautions everywhere, but in UK, if you want to have an MRI scanner, you have to fill a whole questionnaire, and in which they ask you different questions, and one of the questions is, आपने अपनी पूरी जिंदगी में कभी किसी वर्कशॉप में काम किया है? And what's the rationale asked behind that? Because हो सकता है वर्कशॉप में काम करते हुए आपकी आंख के अंदर कोई मेटल को फेरोमैग्नेटिक का पीस चला गया, which you never know, right? So it will go. Or I mean, another problem is the pacemakers. That's another limitation. I think it will come later. I'll come to that. So this is what happens. So in MR scanner room, any chair, even in the surgery, जो वो equipment use कर रहे हैं, that has to be उसमें वो carbon nanomaterials और इस तरह की चीज़ों से बना रहे हैं, वो scissors और जो भी कुछ उन्हें equipment surgeon को चाहिए, because it has to be, you cannot afford any ferromagnetic material at all. And that's the, so what, I mean, one more problem with the MRI is, अगर किसी का pacemaker लगा हुआ है, या किसी के, if anybody has any hip implant or some other implant which has slight ferromagnetic content, you cannot take his MRI exam. I mean, we were doing a course at Hammersmith Hospital in London, and the leading professor, Professor McRobbie, who has written a book, and we go through that quite often. Once I asked him, what happens if a patient is in a very critical situation and you want to take his MR exam, and it's very mandatory because you want to know what's going on in the heart. He says, well, we let him do the MR exam at Hammersmith Hospital in London, but then we keep a team of cardiologists ready outside the scanner room. Right? Why? Because, for example, if you have a pacemaker, right? The pacemaker, it has they have some ferromagnetic content. Or what will happen? It will try to twist. It will try to align itself in North Pole direction. And in pacemakers, what happens is, if there are wirings and all those things, because it's compensating the electrical signals of the heart, so you cannot afford that. Right? Sometimes the dental fillings, they produce some problems as well. Dental fillings, they are, although it's not that dangerous, everybody has dental fillings, but it produces distortion in the images. So अगर आप head का image ले रहे हो और somebody with dental filling, वो नजर आएगा that there is some problem in the image, right? So image won't show a very good contrast. So imaging without ionizing radiation, that's the advantage. Images can be acquired in multiple planes. I said the patient is simply lying in the scanner, and you could acquire the image in any direction, X, Y, Z, any composite plane, no problem. Most images can be obtained without contrast material. CT scan में आपको contrast agent लगाना ही पड़ता है, right? In MRI, you don't need to have any contrast agent. Disadvantages, they are very expensive, not safe for patients with metallic implants, takes longer time to acquire data, patient uncomfort. So people all over the world are dealing with how to improve the quality of MR images with no compromise in the quality. उसके लिए उन्होंने different methods बनाए हैं. At acquisition level, for example, they say we don't acquire data like this. Instead, we'll acquire data in radial projections, or we'll acquire data in spiral projections. That's the data acquisition. Sometimes in reconstruction, you say, well, we don't want to acquire, we want to violate Nyquist criteria. Artifacts, we'll deal with it in post-processing. And then there is parallel imaging, constrained methods, compressed sensing, regularization, non-Cartesian, Cartesian parallel imaging. And my research group is working in all these areas. We at ComSats, we are dealing with all these areas. We are dealing at the acquisition level. We are dealing at the reconstruction level. We are using graphical processing units. We are using FPGA-based designs. We are working with some of the very state-of-the-art universities of the world. I'll explain that in the second part. So, as I said, the fundamental problem of MRI is the acceleration mechanisms, how you want to accelerate that at no cost in the quality of the image. Now, very quickly, I think it has taken longer than we were expecting. So very quickly, I'll give you a brief overview of our research group. So we are medical image processing research group, and I established this research group when I came back from London back in 2013. And we have produced 7 PhDs so far in the past five years, and 6 PhDs are currently doing. A couple of them are sitting here as well, and we have supervised many MS theses, more than 40 perhaps, and more than 70 undergrad students. So we are a very dynamic research group. So currently we are about 28 researchers, postdoctoral scholars, PhD candidates, MS undergrads. Undergrads numbers are lesser because the previous one have graduated and new students are going to come, so the number will increase higher again. But the 4 areas, the 5 areas where we are working on, the first one is the parallel MRI and compressed sensing, in which you violate the Nyquist criteria, and then you want to deal with the artifacts, right? So that's what we are working. Magnetic resonance fingerprinting, it's very state-of-the-art technique, and we are working with the inventors of MRF at Case Western Reserve University, USA. First of all, Dr. Mahmood Qureshi, he's sitting here. He went to Case Western Reserve University. He spent about 6, 7, 8 months there. We brought the technology from there, and we have joint papers, and recently we have filed a patent about our inventions in MRF, and that's something which is fantastic, and that will be the future of MR scanners. We are also working on the chip designing because there's a lot of processing involved. And that's what we were talking earlier, that if you want to do processing, you can do that very efficiently with the help of FPGAs and those sort of systems. And we have developed, I mean, one patent is in final stages, and hopefully it will be granted soon in USA. And I mean, we are working aggressively on ASIC. One paper of one of our MS students was accepted just a couple of days ago in a very good journal. We're also working on parallel computation. That's what Dr. Hassan Shahzad worked on. He's a manager here at National Center for Physics, and he was my PhD student there as well. So we are working on parallel computation, GPUs. We have a dedicated lab. NVIDIA donated us the graphical processing units, and we have set up its lab. We are working on it significantly. Very recently, we have started working on machine learning in MR image reconstruction. And a few of our PhD students are working on it. And when I went to, and we decided to get into machine learning because last year in July, I went to Paris to our annual meeting. There are more than 6,000 professors and scientists and the industrial representatives in the ISMRM conference, and everybody was talking about machine learning and deep learning and its use. And then we decided to use it. So we want to, I've shown machine learning in the middle because it can be used in parallel MRI. It can be used in magnetic resonance fingerprinting. It can be used in parallel computation. It can be used in ASIC designing. It's covering everything actually, right? So we are actively working on it now, and quite a few papers, hopefully they'll be, very recently we have to present 8 papers in the European Society of MRI conference, which is taking place in Netherlands in October, and we have 8 papers, and quite a few of them are about deep learning, how we are working on it. And recently, I'll mention that later as well, but I was invited at Silicon Valley to give a 50 minutes invited talk there in March 2019, where I told them how we are using GPUs, parallel computation, to improve the reconstruction process. But if the parallel computation combined with machine learning, it will be fantastic actually, and we are working in that aspect. We have collaborations. This is a little bit old slide. We are working with Case Western University, where they invented the MRF, and Imperial College London, obviously, NVIDIA, MRB. Dr. Mohammad Kaleem had been to MRB in Germany. So we're working with them. And very recently, which we have not mentioned there, we have developed the collaborations with Geneva Teaching Hospital in Switzerland. They've hosted one of our lab engineer as a fully funded PhD position there. And now they have also, he's working on cardiac MRI there. And they've also agreed to provide one postdoctoral position to our research group, and also one PhD position, one more PhD position will be hosted there. So we are very aggressively working with the Geneva Teaching Hospital as well. At national collaboration, that was, we were talking earlier that with Dr. Samiuddin, that, we do things and we give the technology to the outside world. Why our own national communities or the companies or universities, why they can't use it? For example, why IDC can't use the technology we're using? If Geneva Teaching Hospital has taken the things which we did as in the form of one of the PhD student. So we have recently developed collaboration with National University of Medical Sciences, NUMS, which the old Army Medical College, and also with the AFIRI, Armed Forces Institute of Radiology, and very recently with Punjab Institute of Cardiology as well in Lahore. And at Punjab Institute of Cardiology, they have installed an MRI scanner for cardiac MRI examinations, but they have started learning it, and we have some active research collaborations with them. A few things about our activities in September 2014, she's one of our undergrad students. She went to Edinburgh, and when she gave the talk there, 15 minutes talk at the conference, and when she came down, people asked her, which year of PhD you are in? And she said that, look, I'm 5th semester, 6th or 7th semester student at ComStats University. And they were so amazed that the level of research you're doing in MRI, and you are, all these were the PhDs and the professors. And so, that was quite a big delegation we sent. There were about 7-8 students. They went there for the conference. And Physics Meets Biology conference at University of Oxford as well. And then we went to in Edinburgh in Scotland in 32nd annual scientific meeting, and you could see Dr. Hassan is standing here. He was leading the group, and Dr. Mahmood Qureshi could be seen here as well. So they were, this was our delegation, about 14 students, I think 13, 14 students went from there, and we had quite a good number of papers to be presented there. Then we went to GPU Technology Conference. Dr. Hassan went there at San Jose Convention Center in Silicon Valley. And then, yeah, so that was the GPU, how we are using GPUs for parallel computation. Then we went to at 24th annual meeting of International Society of Magnetic Resonance Medicine in May 2016, and he's Professor Mark Griswold. He's the professor at Case Western Reserve University, USA, and he's the inventor of MRF, magnetic resonance fingerprinting. Their paper was published in Nature, and they're going to. I mean, they are our collaborators as well. So I mean, these are our undergrad students, and so, quite a big delegation. We have about 7 or 8, I think. Then we went to, me and Dr. Mohammad Kaleem, we went to 33rd annual scientific meeting of European Society of MRI in October 2016 in Vienna, Austria. So there we had 21 papers. So we gave 21 talks. I mean, it was one of the biggest representation. So very recently we have signed an MOU between MIPRG and National University of Medical Sciences with the Lieutenant General Imran Majid. He's the Vice Chancellor of NUMS, and he's a good friend of mine because when he was a brigadier I used to go to his lab at Afiri, and then he was more into the fluoroscopy, and then we developed very good research collaboration. So most of the projects we did, and this funding, I mean this MOU was signed because of that project of Holy Quran memorization, which I mentioned in the beginning, that we wanted to have an extensive examination of 80 people, and no other place was able to accommodate us but at CMH it was just one phone call of General Saab and everything was done, right? So it was actually great. Then quite often we have the guest lectures at our university. Imran Majid said, Lieutenant Imran Majid Saab, he has come quite often to our university to deliver lectures. He's a fantastic academician. Not many people from military background, they have that good interest in academia and that good sense of research. So I mean, we are working in quite collaboration, and then we have also Major General Shamariz Khan, he's commandant of Afiri. He delivered a lecture on cardiac MRI in October 2015. I myself gave a welcome speech to UK ambassador telling us about our research activities. He came to Dr. Philip Barton, actually. He was a UK ambassador. They wanted to know about our research activities. And they were more interested because I was a Commonwealth scholar. They wanted to know that the person whom we train in UK, who is contributing to the society here. Then almost every year we have a symposium, medical imaging symposium. So we had a medical imaging symposium in October 2016. So quite good presence of Afiri there and Army Medical College. Then we also gave a talk of Pakistan, that was a computer scientist at Serena Hotel. Very recently in February 2018, we hosted a medical imaging symposium where we invited Professor Robert Dickinson from Imperial College London to give a talk, and there were some other guest speakers as well. So we are we want to communicate science to non-scientific audience, and even to the people who should know about the technological advancements in medical imaging. Very recently in June 2018, I went to Paris, France, and that's the conference I was talking. Everybody was talking about artificial intelligence, machine learning in MRI. So after that, we decided that we should get into deep learning and machine learning, and we have started working on. This is the invited talk I gave at GPU Technology Conference in Silicon Valley, California in March 2019. And it's, by the way, its whole recording is available online. I mean, they have made it freely accessible to the whole world. And just yesterday, they sent me the invitation again. They want me to give another talk in March 2020. I'm not sure whether I'll be able to go or not, but I mean, they wanted me, this year they wanted me to give the insight into their deep learning and machine learning, how we are using it into MR imaging. This is a volunteer being scanned as part of that project we just said. And by the way, in that project, in that research, we found that जो हुफाज थे, उनकी memory cells बहुत ज़्यादा थे as compared to non-हुफाज. Right? So we are doing further investigations. मगर जो हुफाज थे, उनके memory cells सबसे ज़्यादा थे. उसके बाद जो day-to-day Muslims थे, उनके उससे कम थे, और जो non-Muslims थे, उनके सबसे कम थे, who have never been exposed to Holy Quran. And as a Muslim, it's our strong conviction कि hardware अल्लाह ताला ने बनाया है, software Holy Quran भी अल्लाह ताला की तरफ से है. Obviously, it's going to mature your brain. There is no doubt about it. But that was a very unique study, very unique of its own kind. And I mean, उसके लिए हमें we had to scan the Hufaz and quite a lot of work to be done. But we are further investigating it. We have international publications. I won't go into the detail. Many conferences, good international presence, and these are the publications. Here I've given the recent journal papers. This is my research team. Although some of the photographs are not there, but I mean, we are a big research group. Even the students who graduate from us, they are also part of our research group, and they contribute somehow. The last thing which I would like to mention is the first thing when X-rays were invented, X-ray imaging. Do you know one of the basic use? क्या basic use था when the X-rays were invented? In the shoe shops of London. In the shoe shops of London, X-ray machines were used to check if you are a very rich person and you want to have a perfectly fit shoe which perfectly matches to your foot. You should go to a very elite shop. You'll go there, they'll take an MR scan, right? You just Google it and you'll find many videos about that as well. That how do they fit it? Why? Because we did not know the dangers of X-rays at that time, right? So customers expect it. Although we don't know there are any disadvantages of MRI currently, right? But there might be. So as experts, what is our role? What we are doing in our research is we want to minimize the exposure. Even if the radiation is non-ionizing, still we are trying to minimize the exposure, because obviously if the patient is in the scanner for a lesser period of time, he'll be less exposed to the radiation anyway. So as technologists, this is our responsibility, although customers expect it. But we should keep in view the dangers, and that's the slogan we have in our research. With that, I would like to conclude my talk. Thanks very much, and if there are any questions, I'm happy to answer those. And by the way, this is the real-time MRI of two people speaking. They are speaking Chinese language. Thanks, sir.
Learned and heard about the technologies and things which you haven't heard before. And I think this talk gave us better understanding.
Thanks.
What I know.
Thanks.
I have a very simple and layman question. How you compare this MRI with the PET scan?
PET is actually positron emission tomography, and obviously it's nuclear. I mean, it involves the nuclear nuclear isotopes.
Sometimes you have to shift.
Yeah, exactly. Yes. So that's a very good question, actually. The reason for that is we use NMR. NMR is still in use because the problems with MRI was the real-time imaging. Real-time imaging was the problem. But in nuclear medicine, what you do is you can get very clear physiological information. If you want to, for example, know how your stomach is working, or which part of the stomach is cancerous, or what is happening in the intestines. A few years back, you could not even think of using MRI because the scan time was so long. And then you had to use the PET scan and other gamma camera or other nuclear imaging technologies. But the problem there was the resolution. There you don't get very high resolution. But now, I mean, I understand that MIT, they have set up an imaging facility where they have co-registered the MRI with the PET. They get the resolution from the MRI and they get the physiological information from PET. And even at some places they have combined CT with MRI.
I have two comments. First, I think a lot of research is going on in the different areas, but the image processing technology, I will call it a technology because they have developed. So I think this is one of the areas where all over the world people are spending too much money.
Exactly.
Because it's so much application, starting from the defense.
Exactly.
To the health, and you name it, and application is there. So my comment is, if we look at the images now, they have developed so much good algorithms. From very blurry image, they come up with a very nice image.
Exactly.
Also, you are concentrating, as you mentioned, your group is concentrating in this area because there is a lot of work going on, and there is a lot of space.
Exactly.
And there are applications even in Pakistan.
Exactly.
We can use this.
Absolutely. Absolutely. Yes.
So this is one comment. And another is, I think strictly electromagnetism is a mystery for them.
Yeah.
Because, up to now, the different theories, they just, converge there, where there is electromagnetism. And I think that will be the end as well.
Yeah.
And maybe we are, I don't know, maybe we are able to resolve this mystery.
Yes. Absolutely.
So I feel happy to know that you are working in the area, which is, is there, and it will be there.
Exactly. And that's where you could see electromagnetism in play.
Yeah.
I mean, you are using it for a technology. That's great. Thanks.
Sorry to take too much
Yeah.
time for the questions.
If there are any other questions, yes, please. Yes, sorry.
As sir was discussing about the PET, sometimes when there's a surgery which has been done by a patient, and then when he comes for post-op images to see whether there is some residual tissue left or not. MRI, we give contrast, and there's contrast enhancement of that tissue, and we said that, oh, there's some residual tissue left. But at the same time, post-surgical changes, scar tissue, granulation tissue is also there. It at times very difficult to say whether it is the residual recurrence or it is the surgical scar which is present. Then in that case, PET imaging can be done. And our oncologists, then they go for the PET to see whether there are some metabolic active tissues which are present.
And I think you are getting an atomic level, in nuclei level, very micro information there which you can't perhaps get here. Yes.
And one thing I would like to add, that MR spectroscopy is also very advanced. If there is a tumor which is present, if there is some SOL and we want to differentiate whether it's a tumor or it is infection, then MR spectroscopy is very good in that case. It gives us different peaks that take choline and different.
I totally agree. Two of our undergrad students, actually, one of them, she has been taken for a PhD at Dresden University, Germany. She's also working in colonoscopy, spectroscopy aspect. And the other one who's going to Barcelona, she's also working in spectro. So internationally, there is a lot of concentration. And I think at Kazan University, there's an NMR system somewhere. Somebody told me, I don't know.
And then when I was doing my training at FIRI back in 2007, we had this 1.5 Tesla MRI machine. One thing that we have also started this breast MRI imaging. It is also a good technique. You can see the different, whether it's a tumor, but it is benign, malignant, and different peaks. So that is also one of the very good use of MRI.
Exactly. Fantastic. So we had a good radiological perspective here from an expert radiologist. Yes, please.
Dr. Javed Ahmed from NDC, and I work in image processing and artificial intelligence. One picture you showed that in one picture you showed that the receivers which receive the signal are placed at the left side. Are they really actually placed at one side instead of distributed?
No. Actually, that's a very good question actually. Previously, we wanted to have one homogeneous coil. Before the advent of parallel MRI, they wanted to have one homogeneous coil which will cover the whole of the anatomical part. For example, in MRI, you have a specialized receiver coil for heart. You have a specialized receiver coil for knee, because you can't use one coil everywhere. It has to be customized because the signal which is coming out is in millivolts. I mean, it's very weak signal, microvolts or millivolts. So the signal will be attenuated. The receiver should be as close to the anatomy of interest as possible. So previously, they wanted to have a homogeneous coil which will cover the whole anatomy of interest. But now with parallel MRI, with compressed sensing, they want to have multiple coils. At this time, which should be distributed. For example, I think here in Pakistan, it's mostly the 8 receiver coils. I think Madam can tell that. So 8 receiver coils we use for cardiac. In US, I know there are many imaging facilities. They have up to 128 receiver coils for the head, because the benefit you get for having their receivers at all the different angles, you could get any degrees of image, any degrees of freedom. Degrees of freedom increase actually. So it is. In parallel MRI and compressed sensing, in latest techniques, you want to have a receiver coil which will be sensitive to a very specialized area, right? They should not crosstalk with other areas. So this is how the quality of a receiver coil varies as well. A receiver coil which is able to capture the signals very near to it only, that's it. because you want to use that information about the spatial localization while reconstruction. So, I mean, it has to be uniformly distributed, but the area of sensitivity should be very limited for every receiver coil element. I mean, that's one of the area actually we are working on. One of my PhD students, he was supposed to come here, Dr. Omar, he has worked on, the problem is if you are using 128 receiver coils, there's so much data. And most of the data will be redundant as well, and you are going to process it. And in one MR examination, you're talking about hundreds of slices, what you're going to do with it, where you're going to save it. So then comes principal component analysis. When you say that if you do dimension reduction, you have a lot of data available, you retain only the data which contains the most important information before processing it. Exactly, that's where AI will work. Exactly, because you'll be able to extract the features, although we have used the, I mean, because day by day, obviously you want to advance the technology, the receiver coil will be more and more, and obviously you have to deal with the increasing amount of data. For example, in fMRI, when your brain is working and you are continuously acquiring data, imagine how much data you'll have, how you're going to process it. So that's why, I mean, feature extraction and deep learning can help a lot, actually. Yes, please.
Basically, I'm working on development of access system, which discriminate among organic and metallic objects. So my question here is, can MRI differentiate among different materials, or more pinpointedly, can this MRI identify specific materials? For example, water. There is tissue, there are tissues, there are bones.
Yes.
Do MRI...
I mean, the question is very good, but I partially answered it because you can take the MR exam of any molecule which is spinning, which is wobbling, and where the number of neutrons and protons are different, or where is dipole, only those isotopes it will be able to detect. It cannot work for every atom. Right? It will work only for the cases where the protons are wobbling or where the nuclei is wobbling, because that's the fundamental principle of resonance. Right? So, for example, if you want to image sodium in arthritis patients, you have to inject the patient with sodium, some isotope of sodium, which shows that property, right? So that it has dipole present in it, or something, so that it shows some difference, and then in terms of number of protons and neutrons. If that is true, it can be used anywhere. But then obviously, I mean, you have to design, if you are dealing with different types of materials, you have to design special antennas, special receivers, right? And then gyromagnetic ratio will be different, omega will be different, right? So many, I mean, so whether it is worth building all that system, because it's not only the receiver, the signals you got, then you have to process it. It's a long processing, long chain of processing.
Basically, I was asking this question because like there is a limitation for X-ray scanners which are installed on airports, etc. They can only classify among organic, inorganic and metals. But this technique, because this has quite high resolution of images, and also 3D, you also told that it can show without rotating any generator around. If this can be added, this discrimination ability can also be added to MRI, then such equipment can also be used as
in current
scanners.
environments, MRI will be a very noisy addition to the airport. Okay. It will make a lot of noise. It will not be feasible. So technology won't turn into engineering. Because, it's very complicated system. Okay. And to maintain it, and for example, when you come back from, I was coming back from San Francisco. San Francisco, what they have done is everybody needs to be scanned. With CT, it's just a matter of just stand there, in a second you're done. Now, who will control the pulses? And it's not for that use actually. But theoretically, yes, you could do that. NMR is seeing, its use. Okay, great. Yes, please.
You use the equations to generate the dictionary.
Yeah, block equations.
Yeah, it's like a block equation. If I want to deal with the heart, there's also a motions comes in it. So do we have to modify those? It seems like we do.
No,
have to
that's
modify.
that's actually the basic use of MRF. That you'll completely freeze motion. Why? Because you are, you are fundamentally detecting the signal and then you are matching it with the dictionary. So whatever is the dictionary value, you are placing in the pixel. So if there is some motion, it won't.
Those equations can be valid for all part of the body from head to toe if
Yeah.
it's not moving.
Yeah, yeah.
Okay, okay, no.
Because it's not dealing with the parts of the body, it's dealing with the molecules, right?
Okay.
Sodium, potassium, calcium, water, yes.
And if it is for the sodium and all that stuff, we have a different dictionary. For the
Yeah.
sodium, if I want to detect, I have a
Exactly.
I have a different
MRF
dictionary.
technique, exactly. Because you have to do, using those block equations, you have to develop a whole dictionary.
For the
Right.
sodium, it will be
Exactly.
different. For the water, it will be different.
Exactly.
If I want to do do for the heart as well, let's jump toward the new side. I do have to modify the equations, and in this area, I would be more interested if your group will work. I'm just from the Air University. We're also working in the MRF. So if your group can work with us, we can induce some this heart motion, and we do need to do a lot of mathematical work in the model as well. Dr. Pasha is also here with me. He's also very expert in this mathematical statistics area. So we can somehow induce some MRF equation. We can modify those equations by inducing them this motion of a heart, and with that we can generate some dictionary, and then we can work on those.
Exactly. I mean, the fundamental limitation.
Yeah, nobody has worked in that.
Yeah, I mean,
this
I'll
area.
tell you, the fundamental limitation with MRF in Pakistan is we have worked on the computational side. What we have done is we were collaborating with Case Western Reserve University, USA. And all the data we obtained from there, what we did was we used GPU. We defined a parallel platform. And usually the dictionary development used to take 4 or 5 hours. We were able to do that in 3-4 minutes. So that was the processing side, because we don't have access to the MR scanner. We don't have research license to the MR scanner, because you have to, it's not only mathematics. I mean, you have to do many calculations on the scanner as well. Right, so MRI scanner will give you, you have to develop different types of pulse sequences, and those pulse sequences will be used to develop different values.
Usually they use the random.
Exactly, yes. So I
random-
mean, although we are looking forward towards that, we have talked about it with Geneva Teaching Hospital. Hopefully, if our collaborations mature, experimental side will be able to do there. But simulation side, yes, we could do here as well.
Okay. If this work is going on.
Yeah. I mean, we can do that. I mean, it's not because the dictionary, once it's made, it will work for the heart, it will work for the brain, it will work for every part of, because the fundamental molecules which are making all those things are just fat, liver. I mean, fat, muscle, blood, water, whatever. Only those, because the calculations are based upon that.
Okay. Thank you.
Yeah. But it will good to further discuss. And recently, one of the postdoc came from UET Texela. He wanted to work on that as well. So I mean, it will be very good to collaborate with you, and we'll be happy to look forward.
Just thank you.
Okay, great. Okay, so